So for part D, there are three parts. The first part asks us to calculate how far down the object has fallen at the moment it attains its maximum speed. So maximum speed will occur when the net force is zero. I'll explain why that is in part 2, but for now just assume that that's correct. So I have the equation of the net force written down right here. It's mg minus kx is equal to ma. So there are two forces acting on this mass. The first one is obviously gravity, which is always going to be pointing downwards. So that's mg. And then there's the force that the elastic cord has on the mass. That's kx. As we had said in an earlier part, right there, F is equal to kx. And just we can take a note of this. Mg is positive here and kx is negative because ma is pointing downwards, mg is pointing downwards. So mg is in the direction of ma, so we're going to take the downwards direction as positive. And then kx, since it's opposing the motion, that's minus kx. But here, as we said before, the net force is zero, and the net force can only be zero when acceleration is zero. And that's because if we look at this term here, m is never going to be zero. M is going to stay constant. So the only way for the net force to be zero is obviously when the acceleration is equal to zero. So we can make the side of the equation zero to get mg is equal to kx. I have that written again on this side, and we can solve for x to get mg over k, plug in the necessary values, 0.69 kilograms for the mass, 9.8 for the acceleration, and 25 for the spring constant, to get a final value of 0.27 meters. But we have to be careful here, because 0.27 meters is only the length that the cord has stretched. We're worried about the total length of the cord. And the unstretched length we had seen earlier was 0.6 meters. So the total length is equal to the unstretched length plus the stretched length, which we found there, and that's equal to 0.6 meters plus 0.27 meters for a final value of 0.87 meters. So remember, that's the total length of this cord. Okay, so for part 2, we have to explain why this is the point at which the object has its maximum speed. So if you look at this diagram here, the speed, if you just imagine the motion in your head, the speed is increasing up until this point, and then the speed is going to decrease. We can look at the equation to understand why that is mathematically. Mg is going to stay constant all throughout the motion, or the scenario that we're looking at. It's only this term that's changing, or in particular x is changing, right? Because as this mass falls down, x is increasing. So around here, when the speed is increasing, x is very small, and it's not going to have an overwhelming effect on f, right? So the acceleration is still going to be positive. mg is going to be bigger than this term, and the acceleration is going to be positive, so the velocity will be increasing up until this point, and that point occurs when kx is equal to mg, right? And then x is getting bigger. At this point, x is, it's still increasing as it was here, but now kx, the total term, is greater than mg, so the acceleration is negative, and therefore the speed is decreasing, right? So what we have here, this is this turning point. This is when the speed has increased to the maximum point, and right before it starts decreasing. So what we're worried about is right before it starts decreasing. That's the maximum speed. So that's why we're looking at the point at which there's zero acceleration, where it hasn't started decreasing yet, but it has increased to its maximum point. So for part 3, we have to find the maximum speed of the object. As we had said earlier, energy is conserved in this system, so E initial is equal to E final. The initial state we'll have is when the mass is up here, and the final state is when the mass is down here, where there's zero acceleration. I have it redrawn right here. This is the final state that we're looking at. The initial state is just up there. And as we had said in part C, in the initial state, the only energy that's acting on this object is the gravitational potential energy. So that's just mgy. That's not going to change. In the final state, we can, as we had in part C, take this as the zero potential area, because as we had said earlier, we're only worried about the change in gravitational potential energy, and that it really doesn't matter where we take zero, right? And just to make it easier for us, we can take it there. So here we'll say that there's zero potential energy. And the other two factors that are contributing to the energy. We have the object is moving at this point, right? Obviously, because we're looking at the maximum speed at this point. So there's kinetic energy here. We also have half kx squared, the energy that the cord is acting on the mass. So we have half kx squared, the energy of this spring or the cord, and then we have half mv squared, the kinetic energy of the object as it falls down. So that gives us our energy equation. We can just solve for v squared. What I did here was I just subtracted half kx squared to this side, and then I just isolated v squared. And then here I plugged in the values that we found earlier. 9.8 for gravity, 0.87 meters for y, which we had found right there. And then minus 25 for k, 0.69 kilograms for the mass, and then 0.27 squared for x, to give us a final value of 3.8 meters per second. And that ends this question. Thank you for watching.